Paul. Hi everyone. First, my excuse for the poorly designed slides and lack of pretty pictures and things that other people have had. This talk was a fill-in because there was a spare slot in the program and Rusty asked me, did I happen to have a talk up my sleeve? So this is a talk I gave a couple of months ago at the Canberra Linux user group. Now, I've tried to compress it down a bit because at the time that talk took about 2 hours and then continued over dinner afterwards. Because I tried to sort of, show a whole lot of code and things. So I'll compress it down a bit, but to ensure that it gets to the bit that you guys are actually interested in, please feel free to ask questions and, redirect the talk into different areas as I'm going along. So just raise your hand or shout out or whatever. I'm very happy for this talk to be diverted into other interesting areas, roughly related to the topic. Okay, so this is about the journey of taking the ArduPilot autopilot and eventually getting it running on embedded Linux boxes in aircraft and rovers and boats and helicopters, that sort of thing. So I started getting involved with the ArduPilot project a few years ago, and I'd never done any Arduino programming, and at the time it was an Arduino sketch. It was a large Arduino sketch. We've been told by the Arduino Foundation, I think it's called, that they believe we are the most complex Arduino sketch ever built. And we certainly use, on the @mega, we use 243 kilobytes out of the 250 odd K of flash. So we totally fill it. We're down to our last, couple of 100 bytes of RAM out of the 8 kilobytes. So we're really using all the resources, and we use on Copter about 95% of the CPU in steady state. And so it's really pushing the AVR level Arduinos to its limit. So the project has been moving between a number of different hardware platforms over the years. It started off on this little board back in 2009. This was a thermopile-based autopilot, so basically little thermal sensors sensing the horizon. Moved on, this is about where I joined the project at the APM1, which is actually 2 boards sandwiched together. The bottom board is the main APM1, and the top one was called the oil pan. So the oil pan has all the sensors on it, and then a big connector to go through for the SPI bus and I2C bus and all and analog inputs, that sort of thing, which then connects down to the AVR 2560 on the main board. This started off as an AVR 1280, then the later revision of it went to the 2560, doubling your flash size, which was lovely. Then moved on to the APM2, which is just a single board version of the same board. APM 2.5, 2.6 has snazzier case, a little bit better power handling, and starts moving towards external compasses for less interference and new types of connectors. And then this one is, there's actually an intermediate autopilot that's missing there in that diagram because I stole the diagram from someone else. That's this one here, the PX4, which was a big step for us because the first time we'd gone away from a pure Arduino AVR. This is an STM32F4, so it's got, 192K of RAM, 168 megahertz type CPU. So we're onto the ARMs. Still not at the level, no MMU, not enough RAM to run Linux, of course, on something like this. 2-board design again, I/O and main board. It's actually got 2 ARM CPUs on it, a main STM32F4 and then a secondary STM32F1, which is used for I/O. And for fail-safe, in case everything goes bad, the main CPU crashes because somebody put a bug in, and the I/O processor can give the pilot hopefully some degree of control. And if it's a quadcopter, then just gives them the ability to not do much because you can't fly a quadcopter without a stabilizer. Then the next board is this one here. This is the Pixhawk, this is a naked Pixhawk. That's one with a little case on it. And the Pixhawk is just the 100-pin package of the STM32F4, so a bigger one, more flash, a couple of megs of flash rather than 1 meg of flash, which is nice. more I/O connectors on it. You can see it's just covered in little I/O connectors. And so that's the current generation that the community is. There's about 1,000 of those shipped in the last few weeks. And we've got a community of about 50,000 people on DIYdrones.com. So fairly popular little autopilot. But what I'm talking about today is moving from that original 8-bit autopilot through these basic 32-bit. And the next stage is to put this code onto something that brings me back to my roots, which is Linux. And so things like a Raspberry Pi or a BeagleBone Black. And the process of getting our code base, making proper use of gigahertz scale CPUs, hundreds of megabytes to gigabytes of memory, and the issues associated with doing that. So ArduPilot was basically a large Arduino sketch. It had a setup and a loop. How many of you programmed Arduino? Most? Yeah. So you have your classic. I'll bring up a little bit of Arduino code. This is the core code for ArduPlane, the fixed wing variant of our autopilot. At the time, just before we switched over to a new portability layer I'm going to be talking about called APHAL, Hardware Abstraction Layer, where we started abstracting the code to run on the STM32 and Linux and other platforms. And you can see the classic, little setup that gets run once at initialization. That's Arduino style. Then the main loop that just gets run continuously and does stuff. This main loop is basically driven by sensor data coming in from the gyroscopes and accelerometers. So that comes in this plane case. It's sampled at 200 hertz, downsampled down to 50 hertz, and basically it flies the plane at 50 hertz. So every 20 milliseconds it decides what it's going to do for the next 20 milliseconds by looking at what's happening with the sensors, where the pilot wanted the plane to go, where it's actually going, and what it might do to bring those two into alignment. Sorry, question?
Can you talk a little bit about the trade-offs of having a higher or a lower frequency of doing that?
For plane, the 50 hertz is basically because that's the rate that typical hobby servos can be updated, because the only way you can actually make the plane go somewhere else is to send a signal out to a servo and get it to, change the ailerons and the elevator and the rudder to put them in a different position. And your typical hobby servos will only update at 50 hertz, so there's not a lot of point in doing more than that. There can be advantages regarding the attitude estimation, running that at a higher rate to reduce some of the geometric problems you get with, you're basically doing like a little trapezoidal integration, I guess, in 3 dimensions when you're estimating your attitude, and if you cut the corners too much, you end up with a bit of error, but you can compensate for that. So you can, in fact, get, fraction of a degree type accuracy at 50 hertz. The copter actually runs it at 100 hertz because they're not generally controlling servos, they're controlling motors via speed controllers, and they actually send the signals out to those at default about 400 hertz. They run the main loop at 100 hertz just because they can't afford on the APM2 to run it any faster. They're already using 95% of the CPU. Now, there's a variant of the APM code that when it's running on the faster CPUs, it runs it at higher speed. And there's various arguments about whether running it at 200 or 400. Once you get to sort of 200 and 400, then you have to think about, the spin time of a propeller. If it's going around, complete revolution at, 500, 1,000 RPM, something like that, then you think about how much time is involved. If you're giving it a new rate to rotate at every quarter turn, I mean, the propellers come back to you and say, bloody hell, you just told me to spin at that rate, and it's only a quarter of a turn ago, and now you want me to go a different speed? There's limits in the physics of how fast these things can actually change their rates. They've got some inertia. You can't change their speeds that quickly. Plus, if your physics model in the aircraft is assuming that this thing's providing a certain degree of thrust with a certain spin rate, then unless it does a full revolution, it's not really providing uniform thrust. Anyway, so 100 hertz to 400 hertz is the sort of range that these hobby autopilots want to run in, around that. So this is what the code looks like. It's, if you've done any Arduino coding, you'll notice that you can load this up into the standard Arduino, this version of the code, compile, load it onto an Arduino, and it can go and fly an aircraft, which is great. But what if we want to do a bit more? We spend a lot of our time trying to squeeze more and more into this little tiny Atmel, these AVR CPUs. They run out of RAM, we've run out of flash, we've run out of CPU power, and we want to do more and more. People expect more and more from their aircraft. When I first got involved in the project, people were delighted if you took off and landed with the aircraft in the same number of pieces as, at both ends of the flight. That was a successful flight. These days, if it's loitering in a circle, and if the circle is a tiny little bit of ellipsoid, right, that they'll write to you, it didn't do a perfect circle, in a 20-knot wind. Thinking, okay, clearly we have a major bug here. And so the expectations keeps rising in the community, and along with those expectations, it's more resource hungry, the whole process. So we want to make it go faster, we want to use more maths. So this is if I show you the new maths, I can show you some of what it looks like, and we're just switching across, for those of you familiar with Kalman filters, then we've just recently switched over to using Kalman filters. You end up with that sort of thing, right? That's code. Can you see the bug? Generated code, of course, something like 6 hours in MATLAB, crunching to generate all the equations. So this sort of thing does not run on an AVR 2560, at least at any, sort of rate that is useful. 1 cycle a minute is not enough to keep an aircraft stable. So this is where we want more CPU power. Okay, so we originally were using just the Arduino wire libraries, which are the traditional libraries that you get when you're doing Arduino coding. We started moving away from those and basically replacing it function by function with our own, because the traditional Arduino wire libraries have issues that they're mostly synchronous functions. You say, do this operation, write to this port, set this pin, do some operation, and then it returns when it's finished doing that operation. But meanwhile, the CPU is just sitting there spinning, waiting for that operation, like an I2C operation to fetch something from a compass, an SPI operation to get something from a gyroscope. Those types of things, it sits there spinning, waiting for that operation to complete. And meanwhile, your aircraft is sort of, tilting out of control, because those operations might take, tens to hundreds of milliseconds, and you're wasting all that CPU. So we started doing our own library by piece replacing it, and doing asynchronous functions and more efficient functions, ones that were more attuned, better error handling. In the case of a standard Arduino sketch, if you're talking to a compass and the wire going out to the compass, an I2C bus, rattles loose, what do you think your Arduino does? It hangs. It hangs waiting for the response from that compass, because you've asked for a response from that compass, and if it doesn't come back, then we might as well just shut down. That's the Arduino way, at least it was when we were replacing these libraries, and of course that wasn't acceptable for us. Compasses do rattle loose in planes if they're not quite, pinned down well enough. And so we, of course, want to handle that and automatically fall back in the algorithms to alternative navigation techniques without a compass, because we want to keep the aircraft in the same number of pieces after the flight as before. So what we had done here, which really laid the groundwork for what I'm talking about today, is what's called the SITL port. So traditionally with autopilots, you have something called hardware in the loop, where you take an autopilot like this and you connect it via a USB cable to a computer, and you run a FDM, a flight dynamic simulator, a flight simulator on your PC, and that simulator outputs all of the sensor data, accelerometers, gyroscope, barometer, GPS coordinates, airspeeds, all of those sort of things are streamed across the USB cable into your autopilot. Then you have hill versions of your sensor drivers, right? A version of all your sensor drivers that can interpret that stream of data coming from your PC and fake up all the sensor inputs, so the autopilot thinks it's flying a real aircraft when it's actually just flying a desktop, right? It's got a desk job. And so this ArduPilot, you can test the code directly on the board. And that's great in many ways, but it's not so great for debugging. It's not so great for experimenting with algorithms. You have to always have something plugged in when you're doing stuff. So I started by doing something called Tridgell. This was one of my first contributions to the project, which is software in the loop. Basically, an Arduino sketch is just C++. It's C++ with some special libraries, right? So no reason why you can't compile it, with G++ as a desktop executable, as a Linux ELF binary. So you can do that, recompile it, fake up all of the registers and things of the hardware with some C++ horrible classes, and it fakes up how the registers behave, or at a higher level how the drivers behave. And then you can fly that executable with no hardware except your normal laptop. And so I did this Tridgell port early on because it allowed us to do things like this. If I go to our auto test site, which I hope is up, there it is. Oh, we had a failure. So this is our auto test system. Every git commit, looks like we had several build failures. Oh, I'll have to look into those. So every git commit, basically, it will build everything and then put up some red if anything fails like that. It takes about nearly 2 hours now to do all the builds, then it goes flying. So there's flying a quadcopter through a course for a competition course, flying a quadcopter around, faking around my local flying field in Canberra. This is flying the fixed wing plane around that same flying field, driving a rover around a little course. All of those, it fakes up all of that and it flies and drives and checks that the thing flew correctly so it can test our code. And that's possible because of Tridgell. Yeah?
When are you going to make it trigger actual flights?
You can make this same code, fly real planes.
Well, no, when are you going to make...
Oh, Tridgell on every git commit. No, maybe not. Not this week. Yeah, that's right. So this is Tridgell only, but it made it possible for us to have a little AWS image which automatically tests stuff, and that was really cool. It's also great, means you can run the code under Valgrind, for doing static testing. You can run it under GDB. You can single step it. It opens up a whole realm of software engineering that is what I was used to, right? This whole 8-bit Arduino development environment, it was fantastic, exciting to learn all about it, but gosh, it was limiting in terms of the tools and what you could do. So go back to my slides again. So we did the Tridgell port. Now the Tridgell port required that we make all of the Arduino libraries compile, right, with ordinary C++ on Linux. Okay, so it had to all be 32-bit, 64-bit clean, 64-bit pointers, 32-bit because it's a 64-bit kernel I'm running. We had to make sure that we use the stdint types everywhere. So instead of just int, not allowed to use int anymore. If you want an int, you either say int 16, int 32, int 8, whatever, throughout the code everywhere. We made sure that we made sure that we got endianness stuff right, all this sort of thing. So we made the code portable. All right, so most of the code by this stage was portable with a few fdefs around to cope with some of the real Arduinisms, but that was really just a few lines of code out of hundreds of thousands of lines of code. So it wasn't very much. So the next step beyond this was the Tridgell was really done as a bit of a hack. And the next level, Pat Hickey jumped into it and did something called APM, the ArduPilot hardware abstraction layer, where this was done because we were porting to this here, which was the PX4 STM32 running the NutX real-time operating system, which is a free operating system, free real-time design for the STM32. It actually runs on lots of different microcontrollers, but the particular port that we had was the STM32 port. So he designed a hardware abstraction layer which allows us to now isolate all of the operating systems and CPU-specific code into an APHAL something directory. APHAL AVR, APHAL Tridgell, APHAL PX4. And so now porting ArduPilot to a new board is a relatively small task. A guy up on the Central Coast ported to a board called the Fly Maple, which is a STM32F1, 75 megahertz type board over a few-day period. and it's a dirt cheap little ArduPilot board, sells for like 60 bucks, and he's got ArduPilot running on it. So you can do copter, plane, and rover on this little fly maple board, which is fantastic. So that went from our code being incredibly non-portable to start being portable. So these are the ports we've got now. We have APHAL AVR, which is basically our original, Arduino libraries in the HAL stuff. We don't link to the original Arduino wire libraries now at all. We sort of weaned ourselves off them slowly, and we used, function by function replaced. Then once we did APHAL, we actually need a slightly modified Arduino editor, if you like using the Arduino editor, which has a pull down that basically disables linking to the standard wire library and just links to our stuff. So we've sort of cut the umbilical cord to the Arduino, libraries and completely standalone now. The CIDL one is the software in the loop simulator. PX4 Fly Maple is the one I mentioned, the guy up Central Coast. VR Brain, which was the first 32-bit port of APM to a 32-bit hardware ArduPilot as opposed to software. HAL Linux, which is really what I'm talking about today. And very useful HAL Empty. Designed generic, HAL Empty contains like stubs for all the ones. It means when you're doing a new port and you don't want to deal with SPI yet, you can just instantiate the HAL Empty version of SPI, which always returns an error. And it makes doing a port much, much easier. So it's a really useful one. Very much just using, inheritance and C++ classes for the whole thing. So very much drinking the C++ Kool-Aid, I guess. Okay, why APHAL Linux? So why I'm interested in doing a port to Linux? Well, partly it's my roots. I've come from the Linux community, the Linux world, opportunities of giving talks at conferences like this. But I've had Linux boxes on board my aircraft for years now because I have cameras on board doing image recognition. I have data gathering stuff. I want to have an SSH link up into the aircraft so I can do things on the aircraft and recompile the code while it's flying, and we do that. In the competition we actually did, I did fix a bug mid-flight. Didn't tell the other team members who were around me because they might have got nervous about me recompiling and loading new code mid-flight, but yeah, it worked. It's modular. So lots of the complex UAVs, including ours, have an embedded Linux box already, particularly for image recognition type stuff, right? It's really common. And you might do it also for fancy GPS stuff, all sorts of things. You might want a more powerful board on there, a generic embedded board, gigahertz class application board. Having two boards, two ArduPilots, makes the UAV larger and more complex, particularly the wiring. I mean, you end up with stuff like that, lots of wires going between the multiple boards. So integrating it all onto one board, it may not actually be, really lighter or particularly smaller, but it's less complex to have stuff on one board. It allows you to fit it into a smaller aircraft more easily, and really small, light aircraft. Light equals long endurance, so you can do longer flights. So that's nice. It also enables things like having Wi-Fi and cameras and other things directly in the ArduPilot. So enables interesting research topics like doing optical flow-based navigation, where the camera is actually recognizing the flow of the scenery below and doing more accurate navigation based on that. It enables you to try to have a camera that recognizes other aircraft in the sky by scanning around the sky and trying to avoid them, or not, as the case may be. There's chasing. People actually try to build planes that chase other planes and chop the ribbon off the back. And if you're having a little camera on the front where you can track the other plane and zoom in on it and chop its ribbon, great. We did that at the local club, and sometimes they land with chunks out of the tail because they got a bit closer than just the ribbon. It allows for a self-hosted ArduPilot. One of the problems we have in our community is that the development environment is different for macOS, Linux, and Windows, right? And I'd like to actually make the ArduPilot self-hosting so it compiles its own code on the ArduPilot and a web-based development environment, and that will open up the development to a wider range of people, because a lot of our tools now only work on Linux. So if you're a Windows developer with our ArduPilot, you're actually a little constrained. You know, the easiest thing to do is to fire up a Linux virtual machine to get some of the nicer tools that we've got. It also should be a fun hack. So the difficulties of APM Linux. Predictable timing. Autopilots need pretty predictable timing in order to be able to fly. They can't just say, you know, please just hold on the world. I'm just writing the stuff out to disk for a bit. You know, with the plain mind holding, you know, it will tend to fall out of the sky, particularly with multi-rotors. They're really sensitive to timing. It can be difficult to achieve on Linux, or at least that used to be the case, that it was difficult to achieve on Linux. Bus access, latency when you're doing I/O particularly, but even things like I2C, SPI, jitter on interrupts, all sorts of things. And so it's quite unusual that people have devices talking to gyroscopes, accelerometers, barometers, airspeed sensors on a Linux box, and so the drivers tend not to be particularly great for that sort of thing. And they're usually done at very low rates. You know, there's plenty of test sketches for this board called the BeagleBone Black and Raspberry Pi that allow you to do gyroscopes and accelerometers and barometers and things. Probably many of you have run them. How many of you have used a Raspberry Pi with some sensors? A few people? Yeah. And so most people, the example sketches tend to run the sensors at like 5 hertz or 10 hertz, whereas to fly a plane, we want to pull sensor data in at a kilohertz. So we sort of want 1,000 samples a second on this stuff, and if you try to run those standard sketches at 1,000 samples per second, it doesn't really work. Okay, so what are the latencies involved in flying a plane or a copter? This is like a hierarchy of the latencies. Down at the hundreds of nanosecond type level, you've got SPI bus. You know, the SPI bus is, you know, going up and down. The MISO-MOSI pins are MISOing and moseying along at a, you know, 10 megahertz, 20 megahertz. Yes, sorry, Hugh. And that's of the order of, you know, hundreds of nanosecond type speed, those transitions. And that really needs to be handled in hardware. So you need an SPI peripheral that will talk to those devices. For those of you who don't know SPI, it's a bit like I2C in a way, and similar purpose, but much higher rate typically. And it's a, you know, 3 plus N bus, which means you need sort of the MISO-MOSI lines plus a chip select per device. So a separate pin that says, I'm talking to this device now, then I'm talking to that device, then I'm talking to this device. Whereas I2C is just a couple of pins, and the twiddling the pins itself says which device you want to talk to. So SPI can be a lot faster and a lot more efficient, but needs more pins, and you really need to do it in hardware. Up around the 1 microsecond level, you have your PWM, pulse width modulation. That's what this row of pins is, or at least most of them. 14 of the 16 pins across here are PWM pins, pulse width modulation. And they're basically the width in microseconds. You know, 1123 microseconds means a servo attached to that will move its arm to that position, right? And you really need the accuracy of those transitions to be within a couple of microseconds, preferably 1 microsecond. But a couple of microseconds will do the job, and that's the typical sort of jitter you get. And so you get those. Now, I'll talk about the PRUs a bit later, you know, where you do this microsecond stuff, move up the level. There's also PPM sum input. That's the RC input, the pilot controlling the plane. And I know the pilot's movements might be relatively small, but the signals going in are also at the microsecond level. So they're microsecond-like transitions, and they're like PWM, except it fits, you know, 8 or 12 or 16 values on the one pin by just putting them in a sequence and then having a bit of a gap, and then a sequence, then a gap. And SBus is very similar, and they're all about microsecond. Then you've got millisecond stuff going on, which is sort of sensor input. Gyros and accels you want to read at about kilohertz, so a millisecond or so. It's sometimes possible. On these boards, we just read them at a kilohertz, right? We just constantly we've got a little RTOS. It's designed to do millisecond stuff. It has no trouble at all with that, so very easy. On Linux, we're still working out whether we're going to get a little bit of hardware assistance there by asking the sensor chip to queue up sensor readings, like in a FIFO. So we can read like 4 or 8 of them at a time. That's only good if you're only happy to process them in batches. And that very much depends on exactly what type of algorithm you're using for your attitude control and how fast you want to run that loop. So at the moment, the AP Linux port does take advantage of the FIFOs, but I'd like to have the choice of not using those FIFOs and really getting the samples at the kilohertz rate if we can make it with the next generation of AP Linux board. Up at the 20 millisecond type level, you have reads of things like the barometer and the compass and the airspeed and the sonar, if you've got sonar. And they're sort of I2C, SPI for some of them, and analog, just at lower rates. So the bus speed might still be quite high, 400 kilohertz for I2C, 10 megahertz for SPI, but how often you read them is much less. And if you get them a few milliseconds, past 5 milliseconds late, doesn't matter. The barometric pressure 5 milliseconds ago isn't very different from the barometric pressure now. So it really doesn't matter if there's a bit of timing jitter on that. Then up at around the 200 millisecond level, you've got GPS, typically 5 hertz, getting GPS data across a UART. And we're just assuming we've got hardware UARTs for all this stuff. So that's the sort of scale of timings that we have to deal with. So Linux boards. This whole AP Linux project started, as many things in my life do these days, at a hackerspace session. I was at our local hackerspace, Make Hack Void in Canberra. And one of the other hackerspace members had his Raspberry Pi in there, and he said, wouldn't it be cool if I could put ArduPilot in this Raspberry Pi? And I said, oh, that'll be a lot of work. And by the time we left that evening, we had the first port. So because we had AP HAL and, and we thought, oh, it can't be much, maybe we can do this. He had all the sensors and things. He had these I2C, terrible I2C sensors, but they were cheap, like $8 on eBay for a set of sensors. Really cheap sensors. So we did an initial port to a Raspberry Pi running Debian, Raspbian. When I started looking in a bit more, when I got home that evening, I then started looking into Raspberry Pis and looking into the options, and was Raspberry Pi the best thing? What we hadn't got to that day at all was thinking about the output, the PWM output. And his plan was to have a little AVR, like a 328 or something, that communicating over a UART from the Raspberry Pi to do all the PWM output and that sort of thing. I didn't want to go down that route. If we were going to go to AP Linux, if we had a 328 or a 2560 or whatever there, we could just run ArduPilot on it, right? I wanted to be able to get it down to the one for simplicity of software engineering, also because I'd like to see whether it's possible to get as much as we can onto the Linux side of things. So I started looking into Linux-capable boards that might have enough pins on them to be able to do it all itself. And that's where David Buzz pointed me at this board, which is the BeagleBone Black, which is a very cool little board. Incredibly cheap, 50, 60 bucks type thing will get you a BeagleBone Black. A whole lot of pins on it. And it's much more oriented towards the sort of project. I mean, Raspberry Pi is oriented more towards education type stuff. So it's a great board for in classrooms, for video stuff, that sort of thing, hardware, video, encode, decode, wonderful stuff. The BeagleBone is more oriented towards people who might want to be crazy enough to fly planes with Linux. And it's got a number of nice features. One is far more pins here, accessible pins. So, a couple of SPI buses, a couple of I2C buses, more analog pins, more digital pins. But it's also got a really nice little feature as a safety net in case we do find that the core Linux stuff has some difficulties with some aspects of the task. It's got built into the TI chip at the heart of it, it's got a couple of PRUs, programmable real-time units, which are 200 megahertz, which, you know, when I've been dealing for the last few years with the 16 megahertz CPU flying the plane, these 200 megahertz CPUs are a serious grunt. Two little 200 megahertz real-time coprocessors that have 8K of shared memory with the main TI chip and hardware access to a whole bunch of the pins and indirect hardware access to all of the pins. Ben worked that out recently via the memory map. And so that's really cool. So that means that if we run across things that are difficult to do on Linux, we can use the PRUs as like a peripheral that can do stuff for us. And we're thinking in particular the PWM output is likely to go via those programmable real-time units. The downside of the PRUs is that there is no real tool chain for them. You program them in assembler, macro assembler. But you only put little tiny bits of code on them just to do, you know, you don't put a whole autopilot on them. And you do something like just the PWM output or maybe an SPI stack or something like that on the PRU. It also has built-in 8 PWM outputs. We're thinking of not using that, but it's nice to have it. So it can do PWM in hardware. It can also do timer capture in hardware, though no one's written a driver for that yet, for the ECAP, the input side of the ECAP chip on it. And so that can potentially do our radio control input, PPM sum input. So that's the BeagleBone. Of course, it's got a Ethernet port here and a USB port. Unfortunately, only one USB port. We'd really like 2, so we might end up having to have, you know, a little hub or something because we want one for wireless and one for a camera. So that's one downside. It would be nice to have a second USB port on there. So distros and setup, on the BeagleBone, it comes by default with Angstrom, or that's sort of the standard one on the BeagleBone. I've actually found Angstrom quite difficult for general purpose development, and you know, my background with Debian and Ubuntu and previously with Red Hat and others, Angstrom was fairly limited. It was designed to be, you know, a very small distro, which is great. But I found that, you know, once I tried to install some packages, you know, install Zcash, rsync, you know, Emacs, then, you know, Angstrom started showing some signs of pain. And like you install a package and then it doesn't reboot, and all of the root file system is on eMMC, and you can't get at the eMMC unless you can boot, so you reinstall again from scratch. Joy of joy. So much happier. I set it up as NFS root and NFS kernel, so that means everything was coming from my, you know, Linux server over the LAN, which meant I could, you know, do all my editing on my main Linux box and just, you know, it was all mounted via NFS, which was really great for doing kernel hackery, etc. So that's the development environment that I'd recommend. AutoPilot sensors. Okay, so what do you need to turn a generic Linux box like this into a AutoPilot? So an AutoPilot needs a 3-axis gyroscope, 3-axis accelerometer, 3-axis magnetometer, a barometer, a GPS, an airspeed sensor, and a bunch of telemetry ports. So that's basically the standard sensor suite that you would have for a typical AutoPilot. I mean, if you eliminate some of these, you can replace them with other things. You can also deal with a subset, and you can lose some of these. There's quite a bit of redundancy, and we're aiming for even more redundancy. On this AutoPilot here, the current one that we're running, we actually have 2 gyroscopes and 2 accelerometers and 2 magnetometers, and I've been flying recently with 2 GPSs. You know, it's great having the redundancy, comparing the sensors, that sort of thing. For the BeagleBone, we're actually aiming to have 3 of everything, because that's got to be better. And partly because we want to play around with different sensors. Yeah, question?
Do you try and keep, for those that matter, I guess it's all but GPS, do you try and keep the redundant sensors in different orientations and axes?
We haven't. We did consider having the gyroscopes at 45 degrees to each other, and there are some arguments that has an advantage, and there's other arguments saying it doesn't matter at all. At the rate we're filtering them, because we might be sampling them at a kilohertz, but we sample at a kilohertz to reduce aliasing effects, but we actually run it through a 2-pole Butterworth filter, and the typical bandwidth of that filter is, you know, 20 to 30 hertz. And at the 20 to 30 hertz level, once you've gone from a kilohertz down to 20 to 30 hertz, I mean, the amount of information left, if you can just rotate the sensors at the end into the whatever frame, and, you know, it doesn't seem to actually help. So we decided, at the moment, we haven't gone with different orientations because it makes it easier then if one of your sensors fails to fall back to the second one, if having them in the same orientation. And it also makes it easier if you want to use two of them to reduce noise by averaging. That also makes it easier if they're in the same orientation.
I was just thinking you could translate, because it would be a static translation, and then...
You could. We could indeed rotate them, and we would cope if we did that, but we haven't as yet. At the moment, we've had them all in the same orientation. So, a question?
A couple of examples of telemetry report that you use a couple of examples of what you use a telemetry report for.
Okay, well, on my planes, I typically have 3 telemetry ports active. One telemetry port talking to an embedded Linux box on board, right, which we no longer need with this. One talking over a 5.8 gigahertz link, which is then giving me high rate telemetry. So this is what I typically see when I'm flying a plane. And if I just fire up the software simulator of my aircraft, and you'll see what I see while the plane is flying. It's just recompiling the, thanks to Ccache, recompiling that ArduPilot code, and then it'll load up a map, and it'll set it up at, and I can just stick it into auto to do an automatic takeoff, and it will then start flying, and I can list its waypoints and list the geofence, and you'll see it, and then I might do something like this. So this is now flying about my local airfield, right? And this is showing the results from 2 different attitude control systems running in parallel on the same aircraft. So I can run an experiment with a complementary filter for estimating attitude versus a Kalman filter. So my primary one here is a Kalman filter estimating the attitude, and this is a complementary filter estimating the attitude. And this gives me nice graphs of what's going on the plane. All this is coming over telemetry, right? Serial, yeah. It's got an XML-defined protocol. We've got this Python-based compiler that compiles the XML down to lots of different language bindings. So it compiles it down to C and Python and JavaScript and C# and whatever else you might want. And it generates all these language bindings, and then that protocol, so this is all the messages that are coming across in that, and you can see how many. So we've received, I don't know, 273 sys status messages since the plane took off, 270 wind estimation messages. These sort of things are streaming down, and then I can control the plane. So I can do something like, you know, click over here and tell the plane to fly over there, please, right? So I'm now controlling the aircraft and saying, please fly to that point over there instead, and then circle about that point. Or you can set it up to follow you. You know, you can have it on your phone or tablet and say, plane, please follow me. And, you know, wandering along, this plane will just circle above you wherever you go until it runs out of fuel. So that's what you use telemetry for. And you have high rate and low rate telemetry. Sort of you might have it high rate over 5.8, lower rate over 900, lower again if you ham radio stuff, whatever. So that's the sort of thing you use the telemetry for. Yeah?
You said you're averaging between 2 of the input sensors when you got these backup sensors. Do you have instances where one of the sensors is wildly off or something and you have to throw away the data, or do you just have them fail?
So the question was, do we have the sensors going wildly off when we actually switch to the backup sensor? The answer is yes, due to some bugs we've had with the ST LSM303D sensor, which was it was an accelerometer. And just occasionally mid-flight, that accelerometer would decide that all axes are showing 67.5 meters per second. And that really screws with your attitude control when your accelerometer sits fixed. And in that case, it can use the other accelerometer, which is one of the reasons why we have multiple accelerometers on this particular board. We didn't originally, and then we got those sort of failures, and aircraft started falling out of the sky. Test aircraft, these weren't production ones, started falling out of the sky, and that wasn't good, so we got 2. So we thought that would never happen, but it did. So we now got them set up that if that ever happens, it not only switches over to the spare one, but it starts blatting messages onto your screen saying, you might like to land now, something's gone wrong, and it starts beeping, this very distinctive beep, sort of beep, 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 you know, yeah.
With 3 sensors, it's easier, but when you have 2, how do you determine which one is giving you wrong results?
We have some heuristics at the moment, but we're now moving towards a Kalman filter, which has a great statistical method of saying that that sensor is inconsistent with the rest, because there's a lot of redundancy, even with only one sensor each. You know, there's an awful lot of redundancy between gyroscopes and accelerometers and magnetometer and GPS and things. And if basically the Kalman filter can say that that sensor, that axis of that sensor is outside the innovation bounds, you know, outside the likely area, and it can actually start rejecting it. As yet, we don't feed the dual sensors separately into the Kalman, which we could. More CPU power, because bigger matrices and things. Yeah.
More interestingly, if your speed controller fails or your propeller falls off,
yeah.
or a control surface stops responding,
yes.
You're feeding it input, but
yes.
it's not responding.
Right.
Can you detect that pretty well?
We have a couple of things where we try to detect those sort of things. We have things, for example, in the altitude control where we detect that, you know, fail-safe type conditions where it really isn't managing to control altitude, and it goes into like, just try its best, or it prioritizes airspeed or altitude. So it has some, but they're sort of Boolean decisions at the moment, and they're based on a set of heuristics in the code. You know, if we get below this percentage of that target for this period of time, then go into this special mode. You know, there's that sort of thing. And the copter code has land, you know, in case things are going really badly, or try not to crash as heavily anyway. That's right, that's right. It can, or it can basically tell the pilot, take over manually and see if you can handle it. Yeah. That's right, and you know, maybe the pilot, but I'm sure the pilot will think they can do better. But, yeah.
Does your Kalman filter code generator have any computational optimization, or does it
Lots. It's Paul Riseborough, the guy who did the Kalman filter, is really a wizard at this stuff, and he's put a huge amount of effort into making this thing computationally efficient. So we were hugely surprised that on the STM32, it's actually only using, for 100 hertz, using about 10 to 12% of the CPU, which we were really surprised how, because he had estimated that as an approximate, but we were really surprised that we actually achieved that. The compiler almost has a heart attack over it. But, much more, that's right. So it started with this cheap sensor. I'm clearly running out of time. So I'll skip along. Linux I2C, yeah. Scheduling issues. Could we schedule properly? So I started off with the default kernel, of course, lots of scheduling issues. Switched over to the RT preempt, Ingo's work. Huge improvement. We also needed to do things like disable frequency scaling, lock down memory and pre-fault the stack, force I2C to 400 kilohertz rather than negotiating and thinking about 100 kilohertz, just not fast enough for the sensors we had. So basically, Linux, and I was also pleased in chatting to Paul McKenney here at the conference that he also thinks that Linux can do it now. That it really is no longer crazy to think about real-time stuff like this controlling an aircraft with Linux, which is great. So we seem to have started on this at about the right time when everyone else has done all the hard work. And so we've really been quite happy. The next step is this. So this is to build a cape. This is the Pixhawk Fire Cape. This is the first public announcement about it, actually. And open source cape. It's going to be the most complex cape we believe ever built for the BeagleBone, using every pin but 4, and we're still looking at those 4. So normally capes are supposed to just use a few pins so you can have more capes stacked on top. I'm sorry, if we've got our cape on there's no pins left. Or 4. So it has 3 of every type of sensor. And that's because we didn't know which sensors were best. Let's put them all on. Log everything, and then we can actually have a flying platform for sensor analysis. Right? So we can really evaluate the performance of all of these different manufacturer sensors and see if their claims are saying, our sensor's the best, our sensor's the best. Have both in the plane flying along and see which is most consistent with the Kalman filter. Really nice. Lots of I/O ports, same number as on here. 12 PWM outputs. The 2 PRUs are all routed up to get all the pins. Really nice little cape, very well done. All the schematics are open, all open hardware stuff. So there's all the schematic for it. And with lots of power engineering, you can reverse bias the voltage, up to 20 volts and it won't blow up, and all that sort of stuff. Some really good engineering's gone in by various people, Philip in particular. And so that's the cape. There were lots of interesting issues with the actual Linux port, how to measure time, monotonic versus wall clock, etc. Planes fly wall clock, real time, but monotonic is really nice for some other properties, and the two don't necessarily match, and that got interesting. How to delay for a precise period of time. I tried lots of different mechanisms for delaying precise periods of time in Linux, putting a thread to sleep for a precise period of time. How you cope with tight loops, scheduling priorities, what to set the priorities, how many threads to have, how to break things up, how to do UART and I/O threads for storage to the SD card or the MMC. Lots of interesting issues. So what's missing? We need to, hopefully in the next couple of weeks, we'll start fabricating the first capes with all of the SPI sensors on them. Then we'll start writing drivers for the sensors on those capes. Initially in user space, very likely later to be kernel drivers. We've got to write the PWM drivers on the PRU. RC input we've got to get working with a timer capture. Power handling, analog sensors, flight tests, of course. You could actually fly it now with the I2C sensors, but it's pretty low rate and it probably wouldn't fly particularly well. But it should work. In ground tests, it works on a rover. We'd also like to develop the web-based development environment to make it more accessible. So when somebody gets one of these and loads the image, they can just sort of go to their web browser, connect to a wireless access point running on the BeagleBone, edit the flight code, compile, take off, see what happens. Build in the flight dynamics simulator, the flight simulators into it. So it's got self-contained aircraft simulators built into the plane, so you can fly around, in virtual courses, and then take it out, then enable real sensors and fly the real aircraft. All directly built into the little AP Linux board. So that's sort of it. And I think I've run out of time. I was going to show a whole lot of code. Most of the evening at Clug was running through the actual code as to how this works. And you can always check out our code. It's in the it's in master. It's our Git master in ArduPilot. GitHub.com/DIY drones, ArduPilot, and it's in the AP HAL Linux subdirectory in the libraries for the actual port to Linux. So any final questions before I let you go off to lunch? Yep.
You mentioned rovers, you mentioned copters, but
yes.
Single rover,
And traditional helis, yeah.
You mentioned fixed wing.
Yep.
Any contact with the high power rocketry?
Sorry, what was the one?
The high power rocketry wing.
They're quite different. I mean, the stuff that Dale and Keith has done with high-powered rocketry is absolutely fantastic. They're dealing with accelerations of 100 Gs. We deal with sort of 4 to 8 G type accelerations maximum. We have had people fly the APM-based boards at over 100,000 feet, going up in a high-altitude balloon, letting go of the plane. It didn't fly itself up there, but let go from a high-altitude balloon and then fly totally autonomous, fly home and land. And the register, the register, the IT. Yeah, they're running APM, and so their plan is to a high-altitude balloon to 20 kilometres, fire a rocket, go to Mach 2, telling the autopilot, yes, don't bother trying to control that stage of the flight. Then just hold the surfaces level. Then when the rocket runs out, says, okay, get us home, please. And it tells the APM autopilot running one of these, please fly home. And the idea is that it then works out where the hell it is after that rocket, ran out of fuel, and says, okay, it's a long way. Fly all the way home and then land neatly in front of the waiting spectators. We hope. But that will be on this sort of board because of the timescales involved. Later on, I hope it'll be Linux-based boards doing that sort of thing. Boats, submarines. There's people doing APM-powered submarines in Sweden and Japan. There's boats. The rover code that I maintain, somebody just took the unmodified code, untuned, put it on an electric boat, and it worked. It navigated perfectly, and everything worked really nicely, which we were really surprised at. So ArduBoat came for free.
There are some other ships you can buy, like Parrots, for example. Is that already running? Can you today or soon take your code and
Yeah, you mean the AR drone type thing? Yeah, potentially. We already have a version of this board that interfaces to AR drones, so you can modify your AR drone to run our ArduPilot. Actually replacing the firmware, that's a different sort of project. We haven't tried that. It'd be a nice hack, but yeah, potentially. You know, that won't be our focus. We're trying to make much better autopilots than what they've got at the moment in something like the AR drone. That's right, replace their software, but better sensors as well, and more telemetry options, and more capabilities, longer range, you know, radios and this sort of thing. So we're trying to be ahead of their stuff. Yeah.
Please join me in